collection of lectures is just going to be me doing a bunch of example problems with Lagrange multipliers and pointing out a few tricks that I've learned along the way. So there's nothing formally that you're going to be learning in this next collection of examples. In fact, if you want to get a little bit better at these calculations for finding these critical points, or finding rather these points at which you could have maxes and mins, that's what this collection of lectures will be for. So let's just go ahead and get started. I'm just going to have some slides. At the top of each slide will be the function that we're optimizing subject to a given constraint, and I'm just going to go to work. So here I have the function f of xy equals x squared plus xy plus y squared, subject to the constraint x plus y equals 1. So g of xy is x plus y, and f of xy is as given. So I need to set the gradient of f equal to lambda times the gradient of g. The gradient of f is 2x plus y, x plus 2y, which is lambda times the gradient of g, which is just 1, 1. So this is 2x plus y equals lambda, x plus 2y equals lambda as well, and the third constraint, or the third equation we have, is just the constraint equation, x plus y equals 1. Again, put a bracket to the right of these to indicate that you want to solve them simultaneously. Let's call these equations A, B, and C. Here, you can already see one possible technique that we're going to use, which is in one of the equations, I already have lambda as a function of the other two variables, and in the second equation, I have also lambda as a function of those other two variables, and so what I can do is just set the lambdas equal. In this case, it's quite easy, but in some cases, you'll have to solve for lambda and then set those lambdas equal to each other. How's that going to work here? So from equation A, 2x plus y is equal to lambda. That's equation A. Equation B says that x plus 2y is equal to lambda. So that says that 2x plus y is equal to x plus 2y. Now we can simplify. Let's subtract x from both sides, and let's also subtract y from both sides. So this says on the left side x, and on the right side, I'm forgetting about the fact that these were equal to lambda to start with. I'm just using the absolute left side and the absolute right side, and I get x equals y. Okay, great. Now we can plug this relationship back into C. So here's perhaps another note that I can make before we plug that in. So if you use two equations to find a relationship, between the two variables, then plug the relationship in to the unused equation. So since I haven't used equation C yet, that's where I'm going to plug in this relationship that x is equal to y. Okay, so that means that x plus y, which is also x, is equal to 1. So 2x equals 1, or x equals 1/2. We had the relationship that x equals y, so if x is equal to 1/2, that implies that y is also equal to 1/2. So the only point that we can consider is the point with coordinates 1/2, 1/2. Let's go ahead and plug this into the function, even though we can see that there's already going to be a little bit of a problem. So the function's value on 1/2, 1/2 is 1/2 squared plus 1/2 times 1/2 plus 1/2 squared. So this is 1/2 squared 3 times added up, so this is 3 times 1/4, which is 3/4. Okay, now, how can we tell whether this is a max or a min? What's going on here is that the constraint x plus y equals 1, that's not bounded like the first example we did was. So in this example, x plus y equals 1, is this graph that looks like this. So you keep going on forever. And so it could be that the point that you found is just locally a max or a min. So we found this point whose coordinates were 1/2, 1/2. That's right here. How can we figure out whether it was a max or a min? Because I know it has to be, well, it should be one of the two. What I'm going to do is I'm going to plug in 2 points, one on either side of 1/2, 1/2, that's still on the constraint function, and see whether I get larger values or smaller. So let's take, for example, the point 1, 0 is on this curve because 1 plus 0 is 1, and the point 0, 1 is also on this curve. So let's evaluate the function at each of those 2 points. The function f at 0, 1 is 0 squared plus 0 times 1 plus 1 squared, which is 1. And the function at 1, 0 is the same thing, same calculation. These numbers are larger than 3/4, which means, so we know from Lagrange multipliers that if we're going to find a max or a min, it will occur at this point. So there can't be maxes or mins lying somewhere else along this curve, which means since the function evaluated at this point is smaller than other points around it, then that means that this is a minimum. If you wanted to get something lower, the function would have to turn back downward, but then that would mean you would have a local maximum, and we didn't find such a thing. So 3/4 here is the minimum value for this function, and the values keep going up as you travel to other points along the curve. So that's the end to equation to this first problem. There is no maximum for this function.